Hello students, welcome to this topic under Analytical Techniques, Mass Spectrometry. So I'm a lecturer Funman, and this is taken from the reference Organic Chemistry with Biological Applications by John E. McMurray, chapter 11 and 10. So in mass spectrometry, we are trying to use the compounds masses to distinguish from one form to the other. Now imagine we have a baby and an adult. We do not have to look at the picture, but if I tell you, now we have two objects, a baby and an adult, you know that I can use the mass or the weight to distinguish them. The one with a lower mass, which is lighter, must be the baby. The one who's heavier must be the adult. That's simple. So in mass spectrometry, we are using that kind of theory to allows us to distinguish between two or more different compounds that are different. So we know that elements in the periodic table, they are all having different masses, different number of protons, neutrons, and electrons. Oh, and by the way, you know that the last four new elements has been named and confirmed in the periodic table. Who are they? Nihonium, moscovium, tennessine, and oxygen. Right, you have to know them now. They're small to remember, but now the periodic table is complete. So different elements have different masses, and different compounds will have different masses. So take a look at here, the ethanol, simplest kind of alcohol, the one that's safe for consumption, we can drink. Maybe you're underage, don't drink. It has a molecular weight of 46, come about from the addition of carbon having 12, hydrogen 1, oxygen 1. AMU stands for atomic mass unit, and in biological sciences, life sciences or biology for your case, it could also mean Dalton. Dopa is a molecule that's very similar to dopamine, makes you happy, and butorphanol is a kind of morphine type of synthetic opiate analgesic. So in mass spec, we measure the mass or the molecular weight of a molecule as a whole entity, or we can chop it up into fragments and then measure the outcome. Now this picture shows a chicken egg white lysozymes. It says here that it is a small enzyme that attacks the protective cell wall of the bacteria. Now isn't that very oxymoronic? Small enzyme. We know that enzyme is a quaternary protein. Huge is a macromolecule. Your primary structure, secondary, tertiary, and quaternary structure is huge molecule. But you get this kind of oxymoron very often in daily life. Right? Just now I was having a jumbo shrimp noodle. You know jumbo shrimp? In Singapore you call it prawn mee at the hawker center. So it has been confirmed rumors that I am seriously funny. If you don't understand what I just said 10 seconds ago, that means you must be clearly confused. So now that this lysozyme breaks down the cell wall, which is a good thing, right? Cell wall of bacteria, never good. And bacteria dies. Yay, hooray, happy. Aren't you happy? Bacteria dies. No! Okay, remember, bacteria, when they die, the cell wall breaks, undergo lysis. What happens is they could release harmful endotoxins, also known as lipopolysaccharides, that can cause sepsis, that can cause rheumatic fevers, which makes people having diarrhea and all other problems in the body. So that's the reason why people always think that, oh, when you boil water, it is safe to drink. But that's not true. In some places, when you boil water and you drink it, you still get diarrhea. So please confirm it yourself. Now, this small enzyme is huge. Look at the number of carbons, hydrogens, oxygen, nitrogen, and sulfur. Right. We can chop it up and detect the masses. Then we know that, this belongs to the chicken egg white lysozyme. MS is the short form abbreviation for mass spectrometry. Now in biological science, so the multi-TOF spectra of the chicken egg white lysozyme that you have seen in the previous slide looks like this. Okay, huge peaks. Look at the value here, 14 plus thousands, and it goes up to 4 decimal places. You might ask, why does it have to be so accurate? Now think of two person. My height is 1.84 meters. If I have a good friend who's the same height, 1.84 meters, who's taller? People normally think that, yeah, you're the same height, but to me, I think we are different height. So we can go down to 1.84 watt meters, right? Go down deep to the centimeter level, the millimeter level, etc. So TOF stands for time of flight, and this is a very advanced mass spec technique that's not covered in this syllabus for CM1401. Okay. So the peak here, highest peak, is due to the monoprotonated protein. So the protein that we've seen just now, we put in H+ ion because it's charged by the presence of an acid, and this is how we get this number. Now, there are different organic functional groups, very common in your syllabus, and I don't have to read it all for you. You can see clearly, and the parts are denoted in red. So these are very characteristics. When you see them, you recognize, oh, CC triple bond is an alkyne, CN triple bond is a nitrile, right? CO double bond here, there's a ketone, etc. So how can we detect the presence of this functional group in a molecule that's unknown to us, right? Let's say you want to make a structure, you want to synthesize a drug. By mechanism, by theory, we know that it should be that product, but you need to confirm that that's the right thing. So we have to conduct analytical tactics and techniques to analyze this sample. So one of the methods is mass spectrometry. So we think about this is my pure product, we fragment it and see, okay, could there be a possibility of having this fragment from the theoretical product? And how could we determine these structures, right? Because let's say we want to synthesize that product, but in the reaction, it could give us another isomer which has no drug activity. That's a safe case, but what if the other isomer can kill people or causes a lot of diseases? That's even very harmful. So we have to make sure that the mass is the same, right? It has the right molecular structures. And I think mass spec can help us. Now, there are 5 main stages in mass spectrometry in the instrumentation. Again, you don't have to remember what are the engineering parts of it, no need. But you have to know these 5. The first part is when you put the sample inside, they have to be vaporized. Under high temperature, must be inert condition, low pressure without a lot of air particles, because if you have a very high pressure, they will collide and come together again. So when you vaporize it high temperature, you cannot have oxygen there, because if not, you oxidize it, then you get CO2, water vapor, that's useless. And next, after vaporization, you will undergo ionization. And here we bombard a stream of electrons here to bring out more electrons to form cations. Take note, mass spectrometry only detects cations, not anions, cations. It doesn't detect any neutral radicals or even molecules. So we use electrons to knock out electrons, to kick them out, right? So the third stage will be acceleration through a hidden electric field. So we have electric field, 2 panels, positively and negatively charged your panels, anode, cathode, and then we pull the cations at high speed towards it, and then the next step will be the deflection through a magnetic field. When you have charged particles, your B field, then you experience a force, we will deflect it. So here we can also detect the angle of deflection, but what we care here in mass spectrometry will be the detection using a detector or a transducer that will transform the data into a graph you can see from a monitor. And what we care here is the mz value. Mz, mass over Z, mass over charge ratio. This is what concerns us here. And Z, the mass can vary most of the time, but the Z, the charge, is normally 1, because it gets increasingly harder to remove more electrons from a electron deficient species. So to get +1 is easy, to get +2 a bit harder, +3 very hard, and so forth.